So when we left here, we were talking about um, Rich is being very suspicious. Is he now? I don't think he's being very suspicious. We were talking about an experiment that we did. John Dalton, way back in the day. Hold on here. I'm trying to get my picture to take over the screen. There we go. John Dalton had started investigating the atmosphere, and we were talking about boiling water, and we actually took an assessment where we looked at water being boiled, heated, and the gas that it produced. We put it to a flammability test, and it extinguished the flame. So we surmised, many of you surmised, that the gas being produced by heating the water was nothing but water vapor. And that was a correct um, assumption. We know that when we add heat to a solid, it turns into a liquid. When we add more thermal energy, more heat to a liquid, it turns into a gas. So all we were doing was changing the states of matter on water when we put heat to it. Yes, saying steam, water vapor, we're fine. Even if you just said water gas, which I think there were a couple people in some other classes that said that. But the big thing, not even knowing that it was water vapor, we were asked, is the gases produced by adding heat to water and adding energy from a battery to water, are they the same gases? So again, going back to heating the water, we knew it was steam. But more importantly, the evidence that it showed us is it extinguished the flame when we put the gas to the flame. So in the second video, we had a gentleman set up a hydrolysis lab where we applied an electrical current to water with a positive and a negative terminal sticking into the water, test tubes over each one of those, and bubbles came off the terminals. These bubbles produced gas, and the ratio of the gas was basically 2-to-1. And what we did then is we took one gas and we took a match to the gas, and it popped, which was a very mild, but it was an explosion. So we knew one of the gases being produced by hydrolysis was an explosive gas. And then the other gas, we put the match in, and it actually grew brighter in flame. It didn't explode, but the flame grew brighter, and we also blew out the match with the coal still growing on the splint, not the match, a piece of wood. We put the glowing red wood into the test tube, and it lit back on fire. So we knew that the gases being produced from hydrolysis, adding electrical energy to water, were different from the gases being produced by heating the water. Does that make sense? Does anybody have any questions on the test? So it doesn't look like anybody has any questions. I'm only looking at the chat. I don't see you guys, your hands, so put something in the chat if you have a question about that. It is. Some people were a little confused. There were a few students who thought that the gas being produced by heating the water was hydrogen. But again, it didn't meet the criteria. And that wasn't really even the question. The question was not what the gases were, but whether or not they were the same gas. So, when people were telling me, oh, oxygen is produced, hydrogen is produced. That really didn't matter. Even though they talked about that in the video, even they told us in the second video that one of the gases was hydrogen and one of the gases were oxygen. That wasn't the question that was being posed to us. It was if they were the same and what evidence did you have? Okay. So we came up with a molecule, or we know what a water molecule is. Let me see here. Aubrey, are you with us right now? I see you're in here.
Yes.
So Aubrey, what do we refer to water? How chemically, what is water?
It is. That might sound like. Yeah. It's H2O.
Close, but not quite. You got the right chemical, H2O. So I'm going to switch cameras on us here for just a second. So my camera might pop off for a second. Let's see here. Okay. All right. You can all see the new camera angle? Okay. So we have what is called a chemical formula. So water is H2O. Now, when Dalton was, do you guys see that right, or is that backwards to you? When I'm looking at the screen, I see it backwards. Do you see it backwards or written normal?
It's written normal.
Okay. So for some reason, my camera or my computer shows it backwards, but that's fine as long as it's not backwards to you. All right. So when Dalton started doing his experiments, he did not know H2O. Okay. He knew there were two gases that made up water. So what I want you to do right now is there is in the Google Classroom, there is a sheet that is labeled a summary of historical investigations and discoveries into the particles of nature. I want you to read page 1 real quick. Take a second to read it. Meanwhile, I'm going to write a couple things up on the board. Yes. Okay, so it's called a summary of investigation. It's actually a 4-page document. There's 4 different things on there, but look for the one that starts lesson 11, investigation. Or summary. Okay. Excuse me, summary.
It's under molecular models. Okay, thank you. Do we just wait after we're done reading?
Yeah, I'm going to give you guys all just a few more seconds. Just the first page. Okay, so, and I'm just going to go ahead and cover it real quick. A summary of historical investigations and discoveries into the particles of matter. So it says, now we'll revisit what John Dalton and his colleagues were investigating in the 1800s. Last we read, they carried out two different types of investigations with water, both involving adding energy to it. Because remember, heat is energy. It's called thermal energy. When they boiled water, they argued that this did not produce a new substance. But when they added energy to water with a battery, they argued that this produced two new substances that weren't there before. And we actually went ahead and we proved that when we did the lab with the flammability test. They conducted flammability tests and they also measured the density of these gases. The one that exploded had a density of 0.09 grams per liter. This was much less dense than the other flammable gases like marsh gas, which is methane. And the one that caused the match to burn brighter also caused a glowing ember to burst into flames. It had a density of 1.43 grams per liter. So it says here, pause here and take out some common gases and see if you can identify these. Now, if I do that, I'm going to take over your screen here for a minute. Come on. Yep, Sanish is right. Hydrogen, oxygen, but Sanish, did you do that because you knew that, or did you look at the chart already? Sanish is not talking. Oh, looked at the chart. Okay. So if we look at the chart, the first one said 0.09 grams per liter. We come down here, the density is 0.09. There is only one gas on this chart that has a density of 0.09. And we look over here, it's hydrogen. Will cause a flame, or will increase the flame and create an explosion. It did create an explosion. And then the other gas, it said was 1.430 grams per liter. And we look down here and we already know because Sanish told us, we already knew because we've talked about this. It's oxygen, 1.43 grams per liter. It says will increase the flame or cause a glowing ember to burst into flames. So we know that it was hydrogen and oxygen. Thank you for pointing that out for us, Sanish. So Dalton developed a new idea to explain these results. He argued that water particles could be broken into parts that make up each of the two gases. In his model, he assumed that each water particle was made of two similar parts connected together. He called these smaller parts atoms. The model of the water particle, excuse me, I'm a little tongue-tied this morning, he developed contained one hydrogen atom and one oxygen atom. So he drew a water molecule that basically looked like this, using the symbols that I have drawn on the board. He believed that water, hydrogen, and oxygen. Yes. Yes, Yosna?
It's backwards. You can't see it. You can't see it because you're sharing your screen.
Okay, so when I share my screen, it is backwards. Interesting. Okay. Better? Okay. No problem at all. Sorry for the confusion. I'm still a newbie at this. So he drew a water molecule that looked like this. So as we investigate, we learn that water is actually H2O. So all we have to do at this point is add another water molecule or another hydrogen molecule. Would this be a correct representation of water? Or a more correct representation of water? Anybody want to take a guess at that? Okay, Vedant. Nobody's volunteering, so I'm gonna pick you guys out myself. Vedant, are you with us? So would this be what I've drawn right here? Would this be a correct representation of water? Or a more correct than this? This is what Dalton believed water looks like. This is what I'm saying water looks like now. So yes, very. Say again, Jesna.
I agree with Mr. Schiller. I think water should have two hydrogen, one oxygen.
Okay. And sure, movie. It was blurry. Sure. No, I'm just joking. I believe you. All right. What I'd like you to do now is I'd like you to go ahead and go ahead and finish reading the article. Um, is it too confusing if I read it to you? Or are you better if you read it, or do you want me to read it to you? Vedant, yes, it is in Google Classroom. It is the article that is, if we click on week 18, open up molecular models, it is the one that says lesson 11, handout a sum. Mine just says a sum, but it's a summary. If you see pictures when you open up your Google Classworks, it's the one that has all the writing on it. So go ahead and read it. I'm going to, you may follow along with me or just read it yourself. In addition to making hydrogen gas and oxygen gas out of water, other scientists found you can also do the reverse. You can make water out of hydrogen gas and oxygen gas. This happens when scientists combine both gases together and add a small bit of energy, such as a spark or a flame. This causes an explosion. When this is done in a container, water droplets appear on the side of the container. When they did this in a closed system, the mass of the entire system did not change. This showed scientists that you can also put atoms together to make compound particles, water. This was the opposite of what happened when they broke water particles into hydrogen and oxygen using energy from a battery. Scientists named the way that atoms can be rearranged to make a new substance a chemical reaction. Over time, scientists started referring to compound particles like water as molecules. Dalton did additional experiments on more substances to see if they were compound particles, molecules, that could be broken into smaller atoms. These experiments ended up producing the same type of gases over and over again from the many different substances that he tested. This led Dalton to suggest that all of these different substances were made of only a few different types of atoms. At first, he proposed that all of the substances he tested were made of only 5 different types of atoms. The diagram here are replicas of those published by Dalton in 1803. Use the diagrams to see if you could explain how it is possible that just 5 types of atoms could make up these substances. Only 10 substances are listed in the diagram to the right. How many other substances do you think are made of the type of atoms shown on the next page? So again, let me share this. Yep, Shirag. Sorry, I was reading. I did not see your comment. And Alexa, thank you very much for posting the links for me. I appreciate that. Okay, so we look here, and if I enlarge this a little bit, just to make sure everybody can see it well. He had 10 different substances. Water, which was composed of 1 hydrogen, 1 oxygen. Now, again, remember, this is what he believed they were made out of based on his experiments he was doing. So, water, 1 hydrogen, 1 oxygen, marsh gas, methane, 2 hydrogens, 1 oxygen, olefiant gas, uh, acetylene, 1 carbon, 1 hydrogen, carbonic oxide, also known as carbon monoxide, 1 oxygen, 1 carbon, carbonic acid, carbon dioxide, 2 oxygens, 1 carbon, nitrous oxide, 2 nitrogens, 1 oxygen, nitric acid, nitrogen dioxide, 2 oxygens, 1 nitrogen, sulfuric acid, 3 oxygens, 1 sulfur, sugar, doesn't say what kind of sugar, but I'm going to assume at this point we're talking about granular sugar. We had 4 carbon, 1 hydrogen, 2 oxygens, and then alcohol, again, don't know what kind of alcohol he's talking about. There are many different forms of alcohol, but 3 carbon and 1 hydrogen. So the question is, what was the exact question? I'm sorry. If he tested, they were only made of 5 different atoms. The diagram here are the replicas. Use these diagrams to see if you could explain how it is possible that just 5 types of atoms could make up these substances. So what I would like you to do in the chat, go ahead and list why you think you can make up all these different compounds, all these different molecules using just 5 different atoms. Vedant, so have you found the article yet, Vedant? All right, you're not responding, Vedant. You still there? Okay. So if you go to the second page of the article, there are pictures here. You can see my screen, correct? You should be able to see my screen. And I was just breaking down these molecules based on the chart that we have. Oops, it's not here yet. Based on what I have on the screen right here. hydrogen, nitrogen, carbon, oxygen, and sulfur. There are many different ways that you can put them together so you can make multiple substances. Very good, Jesna. Angelina, and how are you doing, Angelina? Different type of atoms in different orders can drastically change the outcome. Very good. The molecules are in different orders and most likely made with different conditions, just like you can bake a lot of different sweets from the same ingredients. Okay, very good. You can make so many different elements because the different concentrations of each molecule. Okay, I'm liking the way you guys are saying these. Very good. So this is very true. So the big thing that we see is, let's take a look at carbon monoxide and carbon dioxide. They are both made from carbon and oxygen. Just its name alone, carbon monoxide and carbon dioxide, tell us, but we see here that one has more oxygen than the other. This one only has one molecule of oxygen, and this has two molecules of oxygen. And we'll learn as we're investigating this, carbon, when I just say the word carbon, that means I have one. Mono means one. Oxide is oxygen. Carbon and one oxygen. So carbon and one oxygen. Down here, carbonic acid, carbon dioxide, di is the prefix for two. So one carbon and two oxygens. So carbon dioxide. Nitrous oxide, also known as nitrous monoxide. A lot of times they don't have to put that there. Just like up here, they have carbonic oxide, but its pure name would be nitrous monoxide. Nitrous oxide is one nitrogen, two nitrogens, one oxygen. So this actually should be called dinitrous monoxide. Two nitrogen, one oxygen, and so on down the road. Um, different ways to put them together, different molecules, atoms. Okay, so very good. It looks like we're having a pretty good understanding of this. Um, Anybody completely lost at this point? Not sure what we're talking about. Okay, Vedant. I'm gonna pull you aside here in just a couple minutes, and we'll talk. See that we got everything. Reese, you understanding? Lauren, you doing good? Good. Reese, are you here? Well, yeah. No, actually, I'm sorry, Reese. You actually commented. I see that. My apologies. Let's see here. Bowie, you're good. Um, Lillian, did you comment, Lillian? Let me see here. Lillian, are you with us? Is this making sense to you? Okay, good. Sanish, eventually, yes. Okay, so Lillian, but it's making sense now. Okay, good. Whoops. All right, we're Sheila, and it's good for you now. Okay, good. Um, I'm good. Avinash, you doing okay? Yep. Okay. Good. So, it doesn't, again, Vedant, I will talk to you here in just a couple of minutes. Uh, Again, here was a list of the atoms. And let me just finish this article out for us. So I'm on page 3 now of the article. He found that molecules of both vinegar and sugar contain only 3 types of atoms. So now we're getting into bigger atoms. He found carbon, hydrogen, and oxygen, but sugar molecules were larger and had more carbon atoms in them than acetic acid, also known as vinegar. One consistent piece of data Dalton collected when carrying out this investigation was the mass of the substances he started with, as well as the mass of new substances that were produced in his experiments. Because the mass of all the substances in a closed system never changed in his experiment, regardless of what new substances were formed, it led him to propose the idea that atoms cannot be divided and cannot be destroyed, even in a chemical reaction. Now, can anybody tell me what that theory is? Atoms cannot be created or destroyed. What was another name for that we've learned? Sanish got it first. Law of conservation of mass. Matter cannot be created nor destroyed, only rearranged. All right, coming back to the article. As Dalton tested more substances, he discovered new types of atoms. He revisited his model to include 20 different types of atoms. By the end of his life, the work of other scientists had contributed to the discovery of additional types of atoms, bringing the total number of different types of atoms to 36 altogether. These type of atoms included ones like iron, gold, copper, aluminum, phosphorus. Atoms are too small to see. An atom is a million times smaller than the thickest human hair. In spite of this, scientists found ways to determine exactly how many atoms made up different substances. Like us, they used investigations with water to figure this out. Dalton originally proposed that a single water molecule was made of one hydrogen atom and one oxygen atom. Later, scientists were able to show that a water molecule must be made of two hydrogen atoms and one oxygen atom. One piece of evidence that supported this was something you may have noticed when you used the battery to add energy to water and saw it produce gas bubbles. Think back to this investigation. What was something you noticed about the rate of bubbles produced in each test tube? Anybody want to take a guess at that? So when we were looking at the test tubes, so we had a cup that had positive and negative. Exactly. There's twice as much hydrogen as there was oxygen. So once they saw that, they started to surmise that the atoms were not equal. So let me finish this out. Really, I just closed. Uh, Hold on a second. let me go here and reopen this. Just closed my reading. Yes, ma'am. Yes. They would explode, but if you did it in a sealed container, you would also produce water. So that's what he was saying in the first part of this. Where was it exactly? Hold on, let me return this back to normal size. He said that, I think it was in the set. Okay, it was in the second on the second page. This happened when scientists combined both gases together, like you just asked, and it added a small bit of energy, aka or also a spark or a flame. This caused an explosion. When it was done in a container, water droplets appeared on the side of the container. So yeah, you're basically creating a chemical reaction again, and as a result, oxygen, hydrogen are chemically combining and forming water. Now, when we start to write out formulas, which we're going to be doing here in the next couple days, you're going to see where the energy has to be put into the chemical reaction at. There's a very specific spot when you write out chemical reactions that will talk about where energy is added or removed at. Yes, right. Well, see, okay. What's going to happen is the gases, again, this is getting a little ahead of ourselves, but once I produce hydrogen gas, it is always going to be found as H2. And when I produce oxygen, it's always going to be found as O2. So the gases floating around in our atmosphere, the hydrogen and oxygen that are floating around in our atmosphere, they are H2 and O2. So if I cause an explosion, the way the atoms will typically create themselves is H2O2. Now, in a lab, I can force H2O2 together to create hydrogen peroxide, like Shrey just said. And yes, Shrey and movie, H2O2 is hydrogen. It's hydrogen peroxide, and we'll get into the reason why we call it peroxide instead of dioxide later. I don't want to get too ahead of ourselves right now. The thing about hydrogen peroxide is if I leave it out for a long period of time, I will lose one of the hydrogens, or excuse me, I'll lose one of the oxygens. It will not stay in the hydrogen peroxide continuously. So hydrogen peroxide is not an indefinite product. It has a shelf life. When I lose that extra oxygen out of hydrogen peroxide, it just becomes regular water. Hydrogen peroxide is not a naturally occurring liquid. Does that make sense? It can only be formed in a lab. Um, yes, there is a liquid form of oxygen when I remove thermal energy from it. When I get it colder and colder and colder, it will turn into a liquid. And I can also turn it into a solid. Extremely cold, though. And every once in a while, if you're driving down the highways and you look at these big, long cylinder trucks, they kind of look like gas trucks, but they're usually white cylinders. If you've ever seen a propane truck, they look like that. Sometimes you'll see it will say liquid oxygen. That is the way we transport oxygen is in liquid form. Okay, let me finish up this reading and then class is over. Um, and then I need to address a couple of issues with some people. Jesna, did that answer your question though? Jesna? Okay, thank you. Okay, this showed scientists that you can also put atoms together to make a compound particle, water, also known as a molecule. This was the opposite. Oh, actually, sorry. I was reading the old article. Um, okay. The bubbles that contain the hydrogen gas were produced at twice the rate and twice the volume as the bubbles that contain the oxygen gas. This was one line of evidence from supporting the idea that water molecules is made of two hydrogen atoms and one oxygen atoms. So this is basically where we came up with the first idea of there being more than one molecule of each type to produce an item. Additional experiments since Dalton's time led other scientists to discover even more types of atoms. For example, in 1939, Marguerite Perry discovered a type of atom that she named francium. This was one of the last type of atoms ever discovered in a natural source. There are now 94 types of atoms that we know of, all of which could be found in natural occurring sources. These few types of atoms make up all the different substances found in our world today. And that's where we're going to leave this at that. Now, we do have up to 118 different elements, different atoms, but over 20 of these are man-made. We create them by slamming particles together in what's called a particle accelerator, and they don't last for very long. None of them are long-lasting, but we do create some atoms. And if we can create them and then join them with something else to make a compound, then they last, but they don't last by themselves. All right. So, what I'd like you to do is go through, don't worry about go away, not you. Don't worry about the lesson or the handout representing Dalton's atom, but I want you to look at the handout on molecular models and go ahead and look at all the handouts. The first one, the common gas, is something you're familiar with. You've already read the summary, but I want you to look at the one on molecular models. Um, just review it, and I want you to be prepared to talk about things that you've noticed in this handout. Tell me, I want you to write down some things that you find are common about all the molecules that you see there. And as for that, class is now over, ladies and gentlemen. I hope you guys had a great day. Vedant, I want you to stay. I want to talk to you for a couple minutes. See if I can figure out. Okay, I'm trying to get off the presenting here. Yes, you can, Sanish.